Okay, I guess we can start. Welcome everyone, and today we are happy to have a talk by Ivan Deddo, and he's going to speak about giant graviton expansion from bubbling geometry. So please start.
Okay, yeah. Thank you very much for the invitation again. I will share my screen here. Can everyone see this?
Yes.
Great. Oops. Just a second. Okay. Okay, yes. So, yeah, this talk will be about deriving the giant graviton expansion from supergravity description. In this paper, or this talk is based on a paper Um, I was on with my advisor, Leo Pandozaius, James Liu, who is also at the University of Michigan, and Robert Seskowski, who's a postdoc in China now. And there are two versions of this paper. There's the, there's the PRL version and a longer archive version. So as we know, the ADS-CFT correspondence gives us a precise duality between certain gravity and quantum theories. And in particular, we have the usual correspondence between n equals 4 super Yang mills and type 2b string theory on ADS5 cross S5. And this will be the main backdrop for this talk. So in this ADS-CFT description, the classical supergravity emerges in the limit of large n. So we can, begin on the field theory side and consider, begin with the infinite n description, and then consider finite n corrections to this. And by mapping these to the gravitational description and interpreting them there, we can get non-trivial information about quantum gravity, for example, and log corrections to black holes. In this talk, I will discuss how to derive and interpret the giant graviton expansion of the half-BPS index, so a field theoretic quantity, in terms of the quantized supergravity description at finite n. So we'll understand these finite n corrections. So yeah, the outline will be first just to review the half-BPS index and its giant graviton expansion, which was discovered several years ago. And then I will describe the LLM geometries in 2B supergravity by Lunin, and Maldacena, which parameterize these half-BPS configurations. And then I will describe how we can quantize the phase space or the moduli space of these geometries. And in the process, by summing up different configurations, we can derive this giant graviton expansion in a new way. And then finally, I'll go over some future directions where this could lead. So the starting point will just be the superconformal index of n equals 4. So the full superconformal index is a sum over states, which is similar to the partition function, except that we have this -1 to the f term with alternating sign, depending on whether the states are bosonic or fermionic. And then in n equals 4, we can label our states by 2 angular momenta and 3 r charges. And we can give them corresponding fugacities in the index that have to satisfy a certain constraint. But in this e to the minus beta term here, we have the anti-commutator of 2 supercharges. So this basically states that are annihilated by this anti-commutator will not have the proper superpartners in order to cancel out in the index, because being annihilated by this anti-commutator is the same as being annihilated by just 2 dagger alone, which means that these states belong to short multiplets that don't have enough states to cancel. And these short multiplets satisfy this particular condition on the charges that depends on the particular supercharge chosen. Um, but so there's a relation between the angular momenta R charges and the conformal dimension. And because the states that contribute are locked into this configuration, into this condition, um, this cannot receive corrections, and the index will be invariant under continuous deformations, including coupling. So we can consider a limit of this, which is the half-BPS index. So for the I guess, just count the half-BPS states, we can take a limit on the fugacities to turn off the angular momenta and only leave on one of the R charges, so the R3 charge here with its corresponding fugacity. And we can do this just by taking a limit of these fugacities, send them to 0, because in this limit where these are very small, only the states that have 0 of these charges will end up giving a large enough contribution to the index. And then in that limit, yes, this will just count the half BPS states. And then the constraint on the conformal dimension turns into this. And the states that satisfy this condition are built from multi-traces of just one of the 3 complex scalars in n equals 4, which we'll call Z. And yeah, the multi-traces meaning just all products of traces of different powers of this C. So we can use combinatorics to compute what the index is. So the expression looks like this, where I've just replaced Q3 with Q. And we can understand this because each term in this product is a geometric series corresponding to all the powers of trace of Z to the n for some particular n inside the parentheses. And yeah, these occur in increasing powers, so they can resum into some generating function that's a geometric series. And then this product would go over all n to build multi-traces, except we know from the Cayley-Hamilton theorem that since these are in the adjoint representation as matrices, the states the traces that have little n greater than n will not be independent anymore. So we don't include these in the counting, and we have this finite n expression for the half-BPS index. So now we can consider, I guess, looking at these, beginning with the infinite n index, and then look at finite n corrections to this. So I guess taking a ratio of finite to infinite, we end up with yeah, just these I guess products that are not present in the finite n case. And there's a identity, which is the Q binomial theorem, which I just wrote down here, that allows us to rewrite the index in this form here. So yeah, it has the infinite n piece plus some finite n corrections in this infinite sum. And this is what will be interpreted as giant gravitons and fluctuations of those giants in the dual theory. And this was based on yeah, this part was found in work by Gyuto and Lee and Imamura a few years ago. Yes, so now I will describe how to interpret this index in 2B supergravity. So we know, and this has been known for much longer, that this infinite n index corresponds to multi-graviton fluctuations in the ADS5 cross S5 description. So we know that yeah, operators in ADS CFT are mapped to modes here, and the single traces get mapped to spherical harmonics on the S5 in this particular representation. And if we have multi-traces, that just maps to superpositions of different graviton, KK gravitons on the S5. So the index at infinite n will just count up these multi-graviton fluctuations. And because this is classical supergravity, there's no limit to this here yet. So this goes to infinity. And then The question then will be what accounts for the finite n corrections on the gravity side. So this is where the giant gravitons come in. So giant gravitons are D3 branes, which wrap um, S3 inside S5 and revolve around on the S5. So I guess we can understand this better by looking at the metric for S5 here in this particular coordinate system. So we have a part of the metric that just corresponds to a 3-sphere, and then this is fibered over top of a 2-sphere. So the giants can wrap this 3-sphere, and then they will sit on this 2-sphere and revolve around at lines of constant latitude. So with theta equals a constant, and then they'll move at this particular frequency that period that depends on the ADS radius. And these giants can occur at any given theta naught. But we will be most concerned with the maximal giants, which are these D3 branes that sit at theta equals 0, so at a pole on the sphere. They don't, I guess, revolve around the S5 anymore at that pole, but they end up having maximal angular momentum actually because of the coupling to the RR field inside the DBI action, so that introduces angular momentum. And yeah, they actually have maximal angular momentum, with that being equal to capital N. And the idea here is that along with these KK modes, which I mentioned before, the giant gravitons and their fluctuations will contribute to the half-BPS index and give us these finite N corrections. And yeah, this was understood, but then we will look at this in a different way. Any questions or anything so far? Is this clear? Okay. So now we can consider interpreting this giant graviton expansion. So we know, I guess, in order to match this back with field theory, we need to know what giants are dual to. So this was shown more than 20 years ago that giants cannot be dual to usual multi-trace operators. They're in fact dual to these subdeterminant operators. So these are products of z's contracted with some antisymmetric Levi-Civitas, and basically in the limit where this, or if we take k equal to n, all of these indices in the Levi-Civitas are fully contracted with these z's, and this just produces a determinant operator that has capital N z's. And this determinant then corresponds to the maximal giant. And if we consider what fluctuations of this giant would be, we can't add in any more z's because these would just have to appear outside the determinant, which would mean that they're just some other product that, or some other trace of z that's related to separate graviton fluctuations. But if we want to oscillate the maximal giant, this seems to suggest we should replace z's with I, so take out z's. So this is a more heuristic argument, but the idea is that the fluctuations of the maximal giant, since they're taking out z's, should decrease the R charge of the configuration. So knowing this, we can look at the giant graviton expansion. And I guess this is a slightly different form of it, because before on a previous slide I showed this. So it's possible to resum this, basically rewrite this part of the giant graviton expansion in terms of q to some negative powers in this more simpler way. And then we can see the different terms now and interpret them, because this term corresponds to the gravitons. This term corresponds to the contribution of m different giants, each with R charge capital N. And then this term will be the fluctuations of these giants, because we can see that this will be like some geometric series in negative powers of q, which correspond to the fact that fluctuations on the giants decrease the R charge. And then we'll sum over all possible numbers of giants. So that's the idea of the giant graviton expansion, which was by Giotto and Lee and maybe others. So more recently, this has been put on, I guess, a bit firmer footing by computing the index from localization. So this is based on work by Murthy uh, collaborators and Lee last year. They showed that we can consider doing a path integral, computing the index as a path integral, where we look at probe grain configurations in supergravity corresponding to these giants, some overall possible giants, and integrate over the moduli space as well as all the possible fluctuations, and weight this by q to the r as in the index. And then using localization, they showed that this integral localizes just to maximal giant configuration. So this explains why only the maximal giants were appearing in this giant graviton expansion. But our goal will be, because this is, I guess this relies on a probe brain approximation where the brain, is treated as some object inserted into supergravity. We know that this should also have some, like, the back reacted description in full supergravity. So the idea here will be to go beyond this probe approximation, just work fully in the moduli space of half-BPS supergravity configurations, quantize these, and then derive the giant graviton expansion in this manner. So next, I will describe the parameterization of these half-BPS geometries in supergravity, and then show how to quantize them. So this parameterization is called the bubbling geometry, or the LLM model, by Lunin and Maldacena. So this is from 20 years ago. So basically, the idea here is that we know in field theory that the half-BPS states again satisfy this condition where these charges are zero. So because of this, we know that the full symmetry group of super Yang mills is broken down. So this SO6 R symmetry turns into just SO4, because we can no longer rotate in one of the directions because the charge is turned on. And then we also know there's another SO4 here, because both J's are turned off. And we also have a time translation symmetry. So this will be the symmetry group. And then Lunin and Maldacena found this parameterization of all solutions that satisfy the symmetry. So again, we have the three spheres here, which correspond to these symmetries, S3 and S3 tilde. And then we also have four more coordinates, t, x1, x2, and y. And the nice thing about this parameterization is that this metric is fully characterized just by a single function, z. So these g's here and these h's are some function depending on z. And this z satisfies a linear differential equation, like so. And so we can add solutions together and such, because this is linear. And also this data here should just depend on boundary conditions on the x1 x2 plane with y set to 0. So we can analyze this boundary conditions, and we find that this requires that in order to have non-singularity of the metric, this boundary condition has to be either plus or minus a half. So in this way, then we can think about these boundary conditions that describe the geometry as being characterized by colorings on the x1 x2 plane, where 1/2 is plus 1/2 corresponds to the white region, and then minus a half correspond to regions. Black corresponds to regions of minus a half. So in this description, ADS is just given by a circle with radius related to the ADS radius. Gravitons are fluctuations of this circle. So this would be like some KK mode of large n, large order. And then we can think about giant gravitons as being holes inside this ADS disk. and the maximal giant will actually sit at the center of the disk. So I guess if we look at the metric, these two spheres actually, well, they grow and shrink depending on position in x1, x2 space. So the S3 inside ADS will shrink over the black region, and the other S3 shrinks over white regions. And we can fiber this, we can consider creating a 5-manifold by fibering the S3 over any black region to give like this 5-dimensional manifold. And if we look at the flux here, we can show that flux quantization through this manifold actually demands area conservation. So basically, yeah, area quantization. So basically, the area of these geometries turns out to be capital N, which needs to be an integer. And here we've introduced some effective Planck's constant that which depends on L Planck. So this constant doesn't necessarily have anything to do with the usual way we think about Planck's constant here. This is more useful because we'll think about these as being some phase space description, where this is like a quanta of phase space. So these were just ingredients we'll need in the analysis. So we can also compute the angular momentum of this solution by looking at the asymptotic form of the metric, the cross terms, the corresponding cross terms in the metric, and we find that J is given by this expression. Wait, sorry, actually. Oh, okay. Can everyone still see my screen? I actually clicked on something. Okay. Good. So this J, this angular momentum here, we can actually find interesting correspondence with the fermions in the harmonic oscillator potential. Because if we make this association where we think about this plane as being phase space, this will exactly match fermions. This like description of a Fermi liquid in phase space, where we have basically n different fermions all moving around in circles in phase space, and it's like an incompressible fluid because of the properties of phase space. So this is a very robust correspondence that's been understood from field theory as well. It will come into play later. Any questions or anything on this?
Well, I have a tiny bit of a question about on the what do you mean by bubbling geometries? How do you motivate? How's the name motivated? Sorry, I've heard them already, but maybe you could clarify.
Oh, I think so. I guess were you meaning that maybe I guess we know the symmetries from the field theory that half-BPS states satisfy, so we expect that the corresponding supergravity solutions will also have these symmetries. And I think by bubbling, I guess it refers to the fact that these S3s will grow and shrink depending on which region of this space that we're in. So like, because these can over white regions, these have like 0 size. And then over like black regions, they have non-zero size. So is that sort of what you were asking? Like where it comes from?
Oh yeah, yes, thanks. I think I see it. Yeah, because well, there are effectively the solution has some topological cycles present. I see.
Yeah, maybe I want to add.
Oh yes.
That in fact there are many classes of solutions that have this property. So these are describing half-BPS states, but there are other solutions that describe, for example, large Wilson loops. So they also are in this class of bubbling. So it's a big class of supergravity solutions, and they have these generic properties, but they describe different operators in the field theory side.
Okay. Yeah, thank you for the clarification there. Any other questions? Okay. So now, I will talk about how we can derive the giant graviton expansion as described earlier in terms of these LLM geometries. So the idea here will be to look at configurations of a giant graviton inside ADS, which I showed before are these basically circles inside the larger ADS circle. And then we can consider fluctuating these, just like how we add KK modes to the, like by adding ripples to this ADS circle. We can do the same thing for a giant to add fluctuations. And then we will, I guess we can quantize these configurations by computing like the classical symplectic form on phase space. So this is based on some procedure, I think, first with work by Witten and Trenkovich, and then some later work that actually did this specifically for type 2b supergravity. And then we can use this symplectic form in the Poisson bracket just to promote these to commutators, and then actually quantize these configurations and sum them, weighted by this appropriate factor which we have in the index, the q to the j. And in the field theory, r corresponds to j here in gravity. So this will be the main approach. So just I guess motivating this idea of quantization, which is called on-shell quantization or covariant quantization. We'll start with just the symplectic form. So we know that if we have some phase space with coordinates qi and Poisson bracket, we have a symplectic form like so. And if we, I guess, want to do the analogous thing for a field theory with continuous parameters, we can basically these q's are promoted to the fields, and then in the theory, and then the sum over indices is integration over space-time. So for 2B supergravity in particular, we have the metric, and using the ADM formalism, we can consider the just the metric on a 4-dimensional slice out of the 5 dimensions, and then this associated canonical or the associated conjugate momentum. And then we can do a similar thing for the gauge potential and the associated 5 form. So then, since we have this very nice LLM description, it's possible that we can rewrite this just in terms of like the boundary data in LLM. Oh, and I should also mention there's a just another thing that is this demanding that this delta A be regular in order to have like some non-singular symplectic form, demands that we restrict to the condition fixed fluxes. Otherwise, we won't have the possibility to choose this gauge. And as I mentioned before, fixed fluxes corresponding to fixed area, and we already expect that in LLM we want to fix the area capital N, right? Because we're working at fixed N and then doing this expansion. So this makes sense. So as I mentioned, taking this using the LLM parameterization, we can write all of these, the metric and 5 form and everything, in terms of just boundary data. So if we think about the case of a single droplet, meaning like, for example, the circle in ADS, this should be specified by some R of phi, the polar coordinate curve that describes the boundary. And we can rewrite the whole symplectic form in this, which was done by Maus and Ridgekopf. It's a rather lengthy derivation, but in the end, we can find that it looks something like this. So we have, it's most naturally written in terms of R squared rather than R, but then we just have the wedge products of R squared at different values of phi appearing here. And then we integrate this over the whole boundary of the droplet. So we can generalize this to the case where we have some configuration that has multiple boundaries, like what was shown here. In this case, we have like 2 different R's describing each boundary. But then one could show that the symplectic forms for separate boundaries don't talk to each other. So we can just like find the full symplectic form just by summing these up for each individual boundary. And I should also mention that I guess in general, if we have some much more complicated geometry that doesn't correspond to some type of ADS or deformation of it, it's possible that we may not be able to use this RF5 parameterization. But in that case, there's also a more general way to write this. But for our purposes, the symplectic form will be enough. So from the symplectic form, we can take the kernel of this and to compute the Poisson bracket associated to this symplectic form, and we find that it takes this form that depends on the derivative of a delta function of phi minus phi tilde. And we also have the fixed area constraint, which turns into this condition on R5. I'm sorry, that should be a little r. So we could use these two conditions, this Poisson bracket and this condition, to quantize the geometry. So the idea will be that we promote this to a commutator, I guess. But before we do that, just as a interesting note, so the this description here, the Poisson bracket, agrees very well with this fermion phase space I mentioned, because if we think about x1 and x2 in the LLM plane as being p and q in phase space, we expect like the Hamiltonian for fermions to take this form, right, where we integrate over phase space over the whole entire droplet, and then we can write this in terms of polar coordinates. And then we can ask what happens if we compute the Poisson bracket of R with H in order to compute the time derivative of R. And then what we find is that this is, plugging this in with this Poisson bracket, we get that this is related to R prime of phi, so the phi derivative of R. And basically this means that the time evolution causes the Fermi surface to rotate around. So basically ripples on this surface will be rotating. And this is I guess what we expect for phase space with fermions moving around in orbits in the harmonic oscillator phase space. So now I guess we'll talk about the actual calculation for quantization. So the first quantization we can implement is just this area quantization. So as I wrote earlier, that the area over 2 pi h bar has to be a positive integer. So from this we get the area of this black region, which should be quantized, and we can recognize that as the gauge theory n. And we also have the giant here, which this white region, the area of the white region should also be quantized in integer units. So then we get we can define this m parameter that's related to r squared. So now we have I guess two different integer parameters that characterize this non-fluctuating solution. And here m is interpreted as the number of maximal giants. So as we continue to put more and more maximal giants down, basically the size of this inner circle will grow. And then this is the m that appears in the giant graviton expansion. So now we can consider what happens if we add fluctuations to the boundary. So we can parameterize these equations for the boundaries with in terms of area preserving Fourier modes. So I guess the most natural thing is to write these as the squares of the radial profiles. For one, because the symplectic form, the Poisson bracket here already has these r squared. But also, if we do it in this way, these Fourier modes will end up preserving the area, which is exactly what we need So yeah, the first mode it should be equal to the original area of the the original size of the non-fluctuated solution. And then we also have that these modes should satisfy some reality condition. And then we can go and do the same thing for the inner circle as well. So if we plug in these mode expansions of capital R and little r into the Poisson brackets here, we get the following relation that the Poisson brackets of these alpha and beta oscillators do not talk to each other, and we also see that I guess they're basically the alphas have a relation that looks like just a usual oscillator commutation relation, and then the same thing for the betas. And then the idea is we just canonically quantize these to promote these to operators, which will be like the raising and lowering operators, satisfying these commutation relations. Does that make sense? Okay. We'll continue then. So the idea now is that we can rewrite our Hamiltonian in terms of modes. So by Hamiltonian, I mean the expression for J. It's just that I guess we can think about this as a Hamiltonian in terms of this fermion description. But yeah, we have the formula for J, which depends on the profile of these droplets, integral over them. So I guess once we do this computation, we can rewrite this as just a integral over the boundaries of the droplets. So we have the boundary of the outer droplet, boundary of the inner droplet, or the inner hole. And then we have some subtraction, which was related to the full area of this configuration in the LM pictures. And now if we plug in the modes, we find this expression. So we can already see that this is giving us the ingredients for the giant graviton expansion, because yeah, this term n appears as an exponent in the expansion. These oscillators, this was already I guess known somewhat before, that just like these A oscillators, these will once we compute the index, will give us a term that looks like this, and this will contribute to the giants. And we can see that there's some minus sign here because, like we expect, the giants are decreasing the conformal dimension, and the KK modes are increasing it. So yeah, as far as computing the actual index, we can trace over configurations. Just take the trace of Q to this J operator, and then yeah, take the trace over states, and then sum over all different giant graviton numbers, which in this case controls the size of the inner circle. So when we do this, basically these products are just like generating functions where this product corresponds to each of the different possible modes we have, right? Because we have modes all labeled by n, and each of them, yeah, will have like a n factor here, or m factor, depending on these indices here. So and then we can, yeah, so product is over the possible different modes we have. And then this factor over here is a geometric series corresponding to the occupation number inside that mode. So if we expand this out, it'd just be, yeah, corresponding to all possible occupation numbers of each mode. So this constructs basically these multi-graviton fluctuations, where you can have any number of gravitons in each possible mode. And then
may I ask? Sorry. May I ask a question? Well, first, I'm a bit confused. It's a general question. So you started with talking about giant gravitons as D3 branes, right? Mm-hmm. But your LLM solutions, just solutions of supergravity without sources or with sources? This is one piece of information. Then you mentioned localization, where you had D3 branes coupled to supergravity. referring to Murphy et al. And
Yes.
now you're just discussing quantizing supergravity solution, which are just LLM solutions, without any mention of D3 branes. So why you need D3 branes at all?
Yes.
So what could you explain that general picture?
Yeah. Thank you for asking that, because I think maybe this wasn't clarified. So yeah, I guess what Murphy did was this a probe brain description, right, where we insert these D3 branes, and we have like DBI action plus super action. But we know that these D3 branes will back react on the geometry. So these correspond to like actual supergravity geometries that can't necessarily be described by just like the probe brain. Because we know that like in this back reacted geometry, that basically approaching a D3 brane, you get something that's like approaches ADS 5, I believe. As you go closer to the deep brane. So there's some geometry there that's not captured by the probe approximation. And we can also think about how I guess the ADS5 corresponds to just this circle here in LLM. So the giant is also a circle with this boundary. And so I mean, roughly, I guess, intuitively speaking, this also approaches some region that's like asymptotically ADS5, and that would be like as we're approaching the D3 brane. So this is like going beyond the probe approximation to this like fully back reacted case, and then these these would I guess the probe approximation maybe could be considered as some limit of this, where we take like the this circle to be like very small. Does that make sense?
Yes, but in a way, this giant graviton expansion is naturally understood as you have D3 branes wrapping cycles, and you have multi-wrappings giving you higher powers over this Q. So in LLM, it's kind of you're basically getting the full expression like what you get in index. You don't need to think of any interpretation of this sum as of these powers of Q as wrapping D3 branes, right? So it's a different picture of the same.
I would think of it as still being related, just because like I guess you mentioned like the multiple wrappings of D3 branes. So this I guess goes back to this area quantization, that I guess one single giant graviton D3 brane in this fully back reacted picture would just correspond to like a little hole is like one quanta of area missing. And then as we add more D3 branes in, the size of this hole grows, basically. So that's how we think about multiple wrappings of D3 branes. I don't remember the technical arguments for this, but I know one can compute the R charges of these configurations and show that it matches with what we expect for giant gravitons in the probe approximation.
Okay. Well, thank you.
Okay. Thanks. Yeah, it's good to clarify that. So yes, I was back in this picture here. So so I was saying how these terms here describe like the this term describes the KK modes, and then we also have the fluctuations of the giant, and like I showed with this heuristic argument, where we can think about taking out z's out of this determinant operator. We expect it to lower the R charge, and then just like how the contribution from these oscillators gives us this, we have a similar contribution from the giants with this -1. So the thing is that this almost reproduces the index, but not quite, because if we look at the giant graviton expansion, this term is actually different. So in the giant graviton expansion, this should end up just being little m. So these modes need to be cut off. So then I guess the question is like, what are we missing in this analysis that that would allow it to describe that would give us like a match with the giant graviton expansion? So I mean, in this we have I guess maybe two possible proposals. So this is one proposal based on this disagreement, that we should cut off the total occupation number of the giant's fluctuations. Now the reason for this justification is that if we consider the radial profile of this inner circle for the giants, it's possible that if we add in many modes to this and oscillate this inner circle, we could add in so many modes that it goes that R goes negative, which is something that shouldn't be sensible in these LLM configurations. I guess in our approximations, since we were considering this as being a a description starting at infinite n and adding corrections, we're still thinking about the ADS circle as being very large, so we don't worry about that. But the idea is that since the giant graviton contribution, I guess the giants could be, we could have this, for example, one giant, which would just correspond to like one quanta of area. So in a certain sense, these are, more quantum. And we should, make sure that the radius of these giants actually doesn't go and create something nonsensical. So with this proposal, if we look at the radial profile of a giant, we have the part that just corresponds to just the integer m describing the size. But then we add in these modes. And if the occupation number of these goes past the total occupation number in all the modes goes past m, it's possible, depending on the phase of this, that radius goes negative. So the idea is that we should demand, this cutoff, that occupation numbers for these modes cannot go past little m. So with this proposal, we find that basically we're doing a counting of partitions because the total R charge of a configuration must be, partitioned amongst these modes, which we can think about as having different weights. And by giving this condition on the total the occupation number, this is a problem of counting partitions into at most m parts. So we're saying that we can't have more than m pieces in our partition. And this is a well-known result from combinatorics that this will give us the correct product for the giant fluctuations. I think another thing what one could do by just looking at this is that it seems that I guess a more a solution to be easier to see would be just if we cut off the possible modes that can occur. So here we were cutting off occupation numbers, but just based on the fact that this product is over possible modes, we could also get the same result by saying that there's some type of mode cutoff, where basically a giant graviton or m giant gravitons cannot support a mode more than the mth mode. But so that gives the same result, but this lacks like geometric interpretation, whereas this proposal has something more geometric. But in some sense, it is nice that these both, no matter like which way we cut it off, we're still getting this giant graviton expansion, which hopefully shows some robustness for this proposal. So that is the derivation for the index. Are there any questions on that? Okay, so that's the main result here. I guess there was some other interesting story, which I guess I have a little bit more time. This is something that's a little separate here, but also gives some interesting insight. That there are other ways to perform quantization. So there's also this other approach called deformation quantization, which is separate than this like on-shell covariant quantization we were doing. In this picture, I guess this is more closely related to fermions, but we can think about I guess this Hamiltonian for the fermions, which we identified with the with J for the LLM space, phase space. Before I think for the expression for J, if I wrote it back here somewhere, we were integrating just over droplets. But now if we can also think about integrating over the whole space, the whole entire LLM plane, just with some function that's a density that can either take 1 or 0. So it's just like a way of rewriting it. And then we expect that due to the evolution of fermions and harmonic oscillator, this density function should satisfy this Poisson bracket equation. And then we can apply a method of deformation quantization to this. There's some constraint on this u, which comes from this classical constraint that u should either be 1 or 0. So basically that u squared equals u. And then we can promote this u to an operator. Think about expectation value of this u density for states, and we find that this expectation of u takes this form. So this is like sort of a quantized density for the fermions in phase space. So this function basically agrees with this Wigner quasi-probability distribution. So we know that we think about these fermions as moving around in orbits in phase space, and we have some incompressible fluid of these, and then the quantum, once we quantize this, it no longer is just some distribution that's just 1 or 0. There's some fuzziness to it. And then the idea is that this can be mapped back into LLM, and we can think about this phase space density as actually describing the data for the LLM configurations. And we end up with some configurations that are interesting because these. So I guess we no longer have geometries in this picture that are just either black or white. I guess these pictures show like the sort of classical configurations you'd expect, and then using deformation quantization, we can look at like these quantum u's, like this quantum density, and we find that basically it's not just 1 or 0 anymore. That these configurations will have some fuzziness, which which basically says that this in this picture geometry is I guess this description of metric where we expect it to be non-singular and such is breaking down. And then we had some other connection to this with where we looked at other ways of thinking about reproducing the index by looking at other configurations of giants and things. But I guess this is just a different method of quantization. And here it's interesting that there's no obvious interpretation of the giant graviton expansion within this this picture, because we get some type of like ring-like configurations that just correspond to like the orbits of these fermions moving around. So it seems that the giant graviton expansion comes out of like quantizing this classical moduli space like we did, rather than doing this deformation quantization. So that was just a aside that we also looked at in our paper. Any questions before I just give a summary and future directions?
So there are other examples of index and giant graviton expansions. You would expect similar story in other cases as well?
Yes, I think that's something that we're interested in looking at. I know for for like other indices, and they're definitely other in other theories as well. They're giant graviton expansions. I think I'll describe this later also, how they're like there's also a bubbling description for quarter BPS and eighth BPS supergravity configuration. So we should in theory be able to do this as well. I'll talk more about that in just like one more slide too. Thank you. Any other questions? Okay. So just as a summary. So we had an expression for the half-BPS index, and we know from work by Gyotto and Lee that this can be expressed as some giant graviton expansion, where we start with the infinite n index and then have these terms that appear to be related to the giant gravitons. And then I guess in field theory though, these finite n corrections were originally due to just like trace relations. So these were something that we couldn't see before on the gravity side, but with this giant graviton expansion, then we can find that these giant gravitons are the things that implement these finite n corrections. And the new thing we did here was that we reproduced this index rather than just using the probe brain configurations. We did this directly in terms of the quantized supergravity geometries. So as far as future work and some other questions. So yeah, first there are some unanswered questions here. I guess in this picture, we basically showed that the counting of these maximal giants leads to the index, but we don't. We in this picture alone, we didn't have motivation for why we should count just maximal giants. I mean, the calculation matches, but yeah, this maybe the interpretation of this is lacking. So we know from localization arguments that these provide a reason that supersymmetric localization just picks out these giants. But yeah, since I mean these are very different methods, it's not as clear how this maps into our picture. So this would be something to explore in the future. Maybe yeah, answer this question. Also, is there a more rigorous explanation for this mode cutoff for the giants? Because I guess we did have two separate proposals for doing this. One was more geometric, but yeah, I guess maybe does this always work if we tried doing this analysis with giant gravitons of other types of indices? Would this cutoff still hold? Maybe only one of them does. And then also as a final thing, which I guess I didn't mention yet, so this giant graviton, as we reduced it, is the form that has the negative powers of Q. So if you remember, there were, I guess, two different forms of the giant graviton expansion. So there's this original form here that had this minus, like basically these alternating sign terms. And we, I guess, re-expressed this in a form that has just like inverse powers of Q. But they're, oops, wait, sorry. But yeah, there is a subtlety that this could introduce some type of convergence issues, because I mean we have both like negative powers of Q and positive powers of Q appearing in the index. So I guess maybe it's possible there could also be like a bubbling interpretation of the signed form of this expansion. This is not quite clear yet, but it's something to consider. And then as far as future directions, as I alluded to, there's also description of the half-BPS states. So, quarter BPS states. So quarter BPS operators are given by multi-traces of two scalars now. We introduce some Y and allow for traces that have both of these scalars. And we know that on the gravity side, there's also this quarter BPS giant graviton expansion. And, sorry, I mean, we know that we have this expansion. We know as well on the gravity side that there's this bubbling description. And there's actually also like bubbling description for 1/8 as well. But basically, the ingredients are here, so we can see whether or not we could reproduce the quarter BPS giant graviton expansion from this bubbling description. And moreover, there are also bubbling descriptions beyond 2B in 11D supergravity, for example. This was also shown by Lunin and Maldacena in the same paper. We can think about doing this analysis for ADS 4 cross S7 or ADS 7 cross S4. I think the fermion description is not as well known there, but yeah, the ingredients are there for the analysis. Yeah, there are other things with like considering other Sasaki-Einstein spaces besides S, besides just spheres. They have some expansions possibly. And then finally, yeah, just as yeah, something else to consider. I mean, we know that there are half BPS, quarter BPS, and eighth BPS bubbling descriptions, but is it possible that there's also a bubbling description for 16th BPS? Because this hasn't been shown. I mean, besides just like trying to do some sort of finite end analysis in the 16th BPS case, it would be very, very nice if there was some description of these 16th BPS states in terms of bubbling, because these 16th BPS opens up a new all new types of features like chaos and fortuity and all these other things that have been talked about more recently. So yeah, just some ideas of where this could lead. I think yeah, I will stop there. Any questions or comments?
Thank you. Yeah. Are there any questions?
Sorry, maybe a stupid question, but when you assume a description of one half-BPS operators in terms of giant gravitons, do you assume any range of R charges, or you assume them to be any, like, for instance?
Any what? Sorry.
I mean, the applicable, like, description in terms of giant graviton is applicable for any R charges, or is there a range of R charges where this description is suitable?
It should be suitable for all I guess by well, so it's a sum over configurations weighted by their R charge. So each of I guess yeah, the giant graviton expansion, if we look at it, is where would I write it again? Yeah. So this powers of Q appearing here are the R charges. So we're like, I guess once we do this expansion, it's like a generating function of all different R charges, and there should be no limit on this because the giant graviton expansion is something that can be just mathematically derived. I mean, from these like Q Pockhammer identities here that we just take the mathematical expression. So this always holds. It's just maybe the question of like interpretation, whether that's always valid, but it seems like it is.
Okay, thank you. Another question: when you consider ADS4S7 and ADS7S4, I guess you can consider like analog of D3, but in terms of M5 and M2 planes. But is the quantization of moduli more or less the same in this case, or like there are some subtleties?
Yeah. So I'm not. Yeah, I don't think the quantization has been done in the same way as for 2B. So I know for 2B this was already this was done like about 20 years ago. But I think for 11D supergravity, I'm not sure that this has been carried out. In principle, it seems like it should be possible.
Thank you.
Any other questions? Could you please comment a little bit more on those operators on the CFT side, which were constructed in terms of these Levi-Civita contractions?
Yes, the subdeterminant.
So you are saying that these are precisely dual to giant gravitons, right?
Yes, they should be. Where was this? Oh yeah. Yeah. So I guess what was the question, like how we can see this duality?
Yeah, a couple of questions. For example, indeed, how do you see that? One thing, another thing. Well, I would say that you can still rewrite this in terms of traces, right?
Oh, okay, yeah. Good. That is a good point. Maybe I should not have said that it was.
Probably there are some operators which are very similar to this one, right? But with some slightly different coefficients. What those are dual to?
Yeah. So in some sense, we could consider this as being some. We can write this in terms of a basis of multi-trace operators. So I guess the field theory description is, I guess, a bit different than the gravity one, because in field theory, I guess we could just count up the multi-traces alone, because I think I mentioned this here, right? That I guess we're just cutting off the traces. So in this field theory picture, these determinant operators are just basically already kind of included in this multi-trace generating function. So we don't have to include them separately. But I think the idea, again, this is something also that is not completely clear. But once we go to the gravitational description, I mean, we're starting like this. We're thinking of this sort of as like a large n expansion, right? Where we start with n equals infinity, and going to finite n. So at n equals infinity, like these are huge operators that basically are I guess classically we expect they may not correspond to just thinking about like these fluctuations of the boundary, that because n is so large, these like these determinant operators are something separate, and that seems to be what the giant graviton expansion is maybe saying. I guess I think still maybe that's not completely satisfactory, but I know that there are other ways of thinking about the giant graviton expansion too is I guess that these I guess giant gravitons somehow like implement this cutoff on the traces, because like once the traces grow so large, we kind of think, or once n grows so large, we think about like this limit on the traces as being something that just corresponds to a different gravity solution. Sorry if that's not completely satisfactory, but
And do you have any idea what would happen in let's say free OM vector model? So it's not like in the adjoint representation, but in the vector representation. Let's say ON or SON. And then normally people, well, I don't know whether you're familiar with this, but there, since we have only one index, then single trace operator is bilinear. Double trace is quadrilinear, right? Because
sorry, go ahead.
Yeah, because you have not matrices which have two indices, but a single index, right? And a color index.
Yeah. So this would be like a different theory, or besides super.
Yeah, it's related to higher spin holography. And I was wondering, well, do you have any idea what? So you can construct an operator where you use Levi-Civita that constructs all these vector indices. So I guess this operator is also somehow like very special. Like, are there any ideas what can correspond to in the bulk?
Yeah, I haven't considered that before. Looking at things in other fundamental representation, for example. Yeah, I guess I'm not completely sure what that would look like.
But this should also be something like non-perturbative, like very heavy, right? Because in large n, the scale dimension, informal dimension is very high, so it should be something like heavy.
I guess is there a particular example you're thinking about where we have I guess something in the fundamental representation, I guess, but sorry, I have not thought that before.
Okay, no problem. Any other questions? Okay, it seems that we don't have any other questions, so thank you very much for a nice talk.
All right, and thank you again for the invitation. I was happy to get this.
Yeah, thank you much. Yeah.
Thanks.